Okay, welcome back. We are continuing example 14.1. We just found or calculated the heat transfer to the water. Now, with that, we can also express this in kilojoules. It just makes it a little bit easier to write out over and over again. So I'm going to go ahead and do that. So in 1 kilojoule, there are 1,000 joules. So this gives me 62.8 kilojoules. Okay, so this is my heat transfer to the water. Now I'm going to go to a second page and continue the problem. So we want to now find, I'm going to put step 4, find the heat transfer to the aluminum. Okay, so remember, heat transferred to the aluminum. Okay, so this will be MAL CAL delta T. Okay, so that was 0.5 kilograms. And again, you'll find this in your textbook. I'm going to go ahead and write it down now, and then we can go look at what I'm talking about. Okay, and then delta T. Okay, so let me show you where we find this specific heat. Okay, so this is section 1. Here. Okay, so this is table 14.1. Okay, so table 14.1 has all of these different substances. Okay, and they're separated into solids and liquids, and then gases. Okay, so in the first one we were looking at water, right? And so our water would be under liquids, and that would give us a specific heat, and these are the different units that it can come in. So we're just going to look at joules. Okay, so for water it is 4,186, like I said. Okay, and then the second one was aluminum, and again, here's aluminum. And then we have our specific heat here. Okay, and again, we're looking at joules per kilogram degrees C. Okay, so that's where you find your specific heat values. Okay, so let's go on. So our heat transfer is going to be, I'm going to go ahead and already convert it to kilojoules. So that's going to be 27.0 kilojoules. Okay, remember that for 1 kilojoule, there are 1,000 joules. Okay? All right. So now I can find my total heat. Okay? So remember, that's going to be those two numbers added. So we found the first one was 62.8 kilojoules. 62.8. And then we add our aluminum, which is 27.0. So our total heat is 89.8 kilojoules. Okay, that's our total heat. All right, so that was all for part A. Okay, part B and C are a little more simple. Okay, it states what percentage of the heat is used to raise the temperature of the pan. And then the same question for the water. Okay, so what percentage of heat? So for the pan, that's the aluminum, we're gonna take this value, 27.0, and divide it by our total heat. Okay, that's what it's asking for. What percentage? It's a point there. And remember to find percentage, just multiply by 100. And you get 30.1%. Okay, can do the same thing for our water. 62.8 kilojoules over 89.8 kilojoules times 100, and we get 69.9%. Okay? All right, so that is all for this example. Okay, so let's go ahead and move on to our next example. Okay, this one, it has a very long introduction. Okay, it states that truck brakes used to control speed on a downhill run do work. Okay, converting gravitational potential energy into increased internal energy or a higher temperature of the brake material. This conversion prevents the gravitational potential energy from being converted into kinetic energy of the truck. The problem is that the mass of the truck is large compared with that of the brake material absorbing the energy. And the temperature increase may occur too fast for sufficient heat to transfer from brakes to the environment. Okay. Calculate the temperature increase of 100 kilograms of brake material with an average specific heat of 800 joules per kilogram degree C if the material retains 10% of the energy from a 10,000 kilogram truck ascending 75 meters in vertical displacement at a constant speed. Okay, so that was a lot, but remember when you're going through problems, just take it piece by piece, okay, and start writing down what you know, okay? So the first thing I'm going to do is I'm going to write down everything I know. I know my mass of the brakes is 100 kilograms. I know my specific heat of the brakes is 800 joules per kilogram degree C. I know the mass of the truck is 10,000 kilograms. And I know my displacement y, I'm going to call it 75 meters. Okay? That's what I know. Now, in this paragraph, it talked about turning gravitational potential energy into increased internal energy and increasing the temperature. Okay, so what that tells me is that my potential energy, or gravitational potential energy, is going to turn into my heat. Okay, Q. Okay. So remember that potential energy is equal to mg times h, or that y displacement. Okay, we can say mgy. Okay. And remember that our heat is equal to mc delta T. Okay? So what we're saying is, or what we want to know is our temperature increase. Okay, that's what we want to know, or delta T. That's what we want. Whoops, that should be a capital T. Delta T. That's what we want to know. So what we're going to do is first solve for delta T here. Delta T will then be Q over MC. And again, our potential energy converts into our heat. So I'm actually going to say mgy over mc. Now remember, these two masses are different. Okay, this is the mass of the brake material, and this is the mass down here of the truck. Oh, I'm sorry, I got that backwards. I thought that didn't seem right. Okay, so since the potential energy is coming from the truck, that means that the mass there will be of the truck. Okay, so we're looking at the potential energy of the vehicle here. And so the heat is being transferred into the brakes. Okay. Okay. So delta T then is going to be our mass of the truck. So that's 10,000 kilograms times gravity, acceleration due to gravity, times our y distance, 75 meters, divided by the mass of the brakes, which is 100 kilograms, times C, which is of the brakes, so 800 joules per kilogram degrees Celsius. Okay, once you plug that into your calculator, you'll find that our temperature increase is 91.9 degrees Celsius. Okay. All right. So that was that question. Now let's go ahead and move on to one more. Suppose you pour 0.25 kilograms of water at a temperature of 20 degrees Celsius into a 0.5 kilogram pan, aluminum pan, off the stove with a temperature of 150 degrees Celsius. Assume that the pan is placed on an insulated pad and that a negligible amount of water boils off. What is the temperature when the pan and the water reach thermal equilibrium a short time later? Now that is going to be a key thing to note. So this one again is a little bit longer, so I'm just going to go ahead and get it started in this video. So my mass of water, I guess I can put it up here. Mass of water is 0.25 kilograms. My temperature of water is 20 degrees Celsius. My mass of aluminum is 0.5 kilograms. And my temperature of aluminum is 150 degrees Celsius. Okay. Now, when it states that our system is going to be at thermal equilibrium, okay, our temperatures will eventually be the same, right? So T final will be the same for the water and the aluminum, okay? Then our heat exchange will stop. Okay, so if they are at the same temperature, our heat exchange will be no more. Okay, so our Q of the hot substance, so I'm just going to say the hot substance and the Q of the cold substance should equal to 0. It'll sum to 0 eventually at equilibrium. Okay, another way of stating this is no, actually, this is good. This is good. Okay, so at equilibrium, we have that the heat exchange will stop. Okay. So what we're going to need to do is find both the Q hot and the Q cold, and then plug them into this equation and solve for our final temperature. Okay, we have initial temperatures of both of these substances, but we need to find their final temperatures. Okay, so we're going to go ahead and stop the video here, and then I'll continue with this one in the next video.